In this video, we're going to talk about the simple linear regressions analysis of variance. So let's just recall what the simple linear regression model is. We have yi equals the intercept plus the slope times xi plus some model error, right? For I equals 1 to n. Okay, and in this analysis of variance, this is a hypothesis test that we're talking about. And what are we testing? We're testing whether or not there is a significant linear relationship between yi and xi. And remember, in the simple linear regression model, there's only one xi. There's only one regressor variable, and there's only one response variable. So what we're testing is basically, is this beta 1, is this slope not 0? All right, if it is 0, then this term basically goes away and yi is not significantly related to xi. But if it's not 0, then there is potentially a significant relationship between x and y. Okay, so that's what we're going to talk about here. In this discussion, it follows directly from our discussion on partitioning total variability. Okay, and in that conversation, we talked about the sum of squares total, which is the sum of each yi minus the mean of the y's squared. That equals the sum of squares due to the regression, right, which is the sum from yi hat minus the mean of the y's squared plus the sum of squares residual, which is the sum of yi, so the observed response variables minus the predicted response variables squared. Right? And it turns out if you make the normality assumption, so the assumption that these model error terms are normally distributed with mean 0 and variance sigma squared, if you make that normality assumption and then of the assumption that xi's are fixed, that means that, due to the properties of the normality assumption, that yi would also be normally distributed. And then when you sum up normal distributions like this, then you get a chi-square distribution. So it turns out that under this normality assumption, starting with SS residual, the sum of squares residual, if you take the sum of squares residual and divide it by sigma squared, or the variability of the model, this turns out that this is a chi-square distribution with n minus 2 degrees of freedom. Okay. Additionally, if you add on the assumption that beta 1, or the slope, equals 0, so this is an additional assumption, then the sum of squares due to the regression divided by sigma squared is also a chi-square distribution with degrees of freedom 1. Okay, so I want to take a break here and talk about these degrees of freedom, and notice that the degrees of freedom are also being partitioned in a very similar way that we partitioned our variability. So let's talk about that. Partitioning of degrees of freedom. All right, so starting with the total degrees of freedom, we have n minus 1, which is the number of data points minus the 1 degree of freedom that's used to estimate our sample mean y bar. This equals the degrees of freedom used for the regression, which is, in this scenario, it's just 1, right? Because we have one parameter that we're talking about here is the slope beta 1. Okay, so the degrees of freedom here that's used to estimate the slope plus the degrees of freedom for the residual, which in this case is n minus 2, which is the number of data points minus the 2 degrees of freedom used to estimate beta naught and beta 1, which is the intercept and slope. Okay, so we can see that this relationship is true. N minus 1 does equal 1 plus n minus 2. And the purpose of this partitioning is to provide the foundation for the hypothesis test that we're interested in, which is whether or not that slope, beta 1, is equal to 0. So let me go ahead and write down that hypothesis test. We're building up to testing the null hypothesis is that the slope is 0. Let me scroll down. And the alternative hypothesis is that the slope is not equal to 0. All right, so we're almost there. We're almost ready to go ahead and give that analysis of variance, that hypothesis test. But before I move on to provide the test statistic for that test, let's talk about what this hypothesis test is and what it isn't. It's very common for students and people who aren't students actually to misinterpret the results of this hypothesis test that I'm about to show. So it's important to remember what this test is and what it isn't. First, if you were to reject the null hypothesis, and say, you know what, there's evidence that there is a linear relationship, you have evidence for the alternative that there's a linear relationship between x and y. It's really important to know that that doesn't tell you anything about the quality of the fit. Okay, so for example, you could have data that looks like this. Just a random scattering of data, and then maybe there's like 1 or maybe even 2 outliers. Okay, and then when you run a least squares regression and you try to get the best fit, the regression line looks like this. And it's saying, okay, yeah, you know what, this beta 1, the slope of this, or B1 when you estimate it, the estimate of beta 1, B1, it's significantly not equal to 0, right? And so you conclude that there's a significant linear trend, when in reality, this may be not a good fit, right? So it's really important to remember that the fit is not discussed in this hypothesis test. The quality of the fit is not discussed in this hypothesis test. All right, so let me go ahead and erase this. Another common misunderstanding with this hypothesis test is that a student or someone who is running this test will fail to reject the null hypothesis, right? And they'll say, oh, you know what, there is not enough evidence that there is a relationship between x and y, right? And what you need to remember is that this test is only testing for a linear relationship. So there may be a strong relationship between x and y. So for example, say x and y, this is their relationship, right? If I were to plot my data, right? And we can very clearly see some sort of relationship here where x and y, they go up and then down together and then up and then down together, right? Definitely some sort of relationship between x and y. But then when you ran your model, you have a fitted line that looks something like this, and it's completely flat. Your estimate of the slope, it is approximately 0, right? So you feel pretty good about the fact that you just failed to reject that null hypothesis, and then you incorrectly conclude that there's no relationship between x and y, when in reality all you can conclude is that there's not enough evidence for a linear relationship between x and y. Okay, so those are the two biggest kind of misconceptions regarding this hypothesis test, so you want to be careful that you don't fall into those traps. All right, so now let's go ahead, let's talk about how do we do this hypothesis test. What is our analysis of variance look like? And a lot of times you'll see this analysis of variance written using the acronym ANOVA. All right. So we usually write our analysis of variance test using a table, starting with the source, then the sum of squares. So I'm going to build this table off this way, but let's go ahead and just get started with the source and sum of squares. The first source we want to talk about is the regression. All right, then we have the residual. All right, and then we have the total. All right, so the sum of squares for the regression, SSREG, is the sum of yi hat minus y bar squared. The sum of squares residual is the sum of yi, our observed values, minus the predicted values squared. And then the sum of squares total is the sum of each observed value minus the mean squared. Right? And then the next column is our degrees of freedom. Right? And we just talked about those guys. So the regression degrees of freedom in this simple linear regression is just 1. The residual degrees of freedom is n minus the number of parameters I have, which is 2, beta naught and beta 1. And our total degrees of freedom is always going to be n minus 1. All right. All right. The next column is called mean squares. Mean squares. And a lot of time you'll see this written as MS. In general, what you do to find the mean square, so starting with the mean square for the regression, you take the sum of squares for the regression and then you divide it by the degrees of freedom for the regression, which is just 1. So in general, the mean square is the sum of squares divided by the degrees of freedom. All right, so the mean square for the residual is just going to be the sum of squares for the residual divided by n minus 2. All right, so then our final column F, our F statistic, is the mean squared from the regression divided by the mean squared for the residual. Okay? All right, so then this quotient, the mean squared regression divided by the mean squared residual, this follows an F distribution with degrees of freedom 1 and n minus 2. All right, and so, why is this an F distribution? That follows directly from these sum of squares being chi-square distributions, which follows directly from that the error term is a normal distribution. So you need that normality assumption in order to later have this F distribution assumption. All right. And before I move on to actually calculating this, let's think about what is this F distribution? What is this F statistic? If we think about what an F distribution looks like, okay, it's like a skewed distribution looking like this. The mean squares of the regression, if this is a really large number, right, compared to the residual, then that means that the majority of the variability is explained by the regression, which would yield a large F statistic, right? An F statistic in the tail. So if the mean squared regression is, much larger than the mean squared residual, then you're going to have a big F, right? So, and that big F value, it's going to say, maybe this distribution is unlikely. And why is it unlikely, right? Why am I observing an unlikely F value? That goes back to our assumption when we said that SS regression is a chi-square distribution, we needed that assumption that the slope equals 0, right? So if the slope is not equal to 0, then this all falls apart in this f distribution. It's not good, right? And that's why we're observing an unlikely f value, right? If this is true, right, this distribution that the slope is equal to 0, then we'll probably observe an f value that's likely, right, in this area over here, a likely f value, right? So a likely f value is going to be a small f value. And this small f value is going to occur when the ms for the regression is comparable to the ms of the residual. In other words, it's just not much bigger, right? So it can either be less than or it can be equal to. And in that situation, the residuals are explaining a lot of the variability rather than the regression. Okay, so that's the intuition behind this F test. Okay, so let's go ahead and let's do an example. I have some data here. Now, we don't usually, run these F tests nowadays. We don't do this by hand. Back when I was in grad school, we definitely did it by hand, using an old F table or whatever. But now we have, these great computer programs, and nowadays most people never do this by hand. They depend on Excel or some other computer program to do this hypothesis test for them. So let's talk about how to use Excel to do that hypothesis test. I have some data on 2010 life expectancy and the income per person, right? And what I want to know is whether or not income is significantly linearly related to life expectancy. All right, so if I'm up here in the home bar, I need to make sure I go over to where it says data and go to my data analysis toolpack and scroll to where I see regression, press OK. The Y variable here, the Y range is going to be my life expectancy. So I'm going to click on that label. I'm going to press Control Shift down, and that'll highlight all of my data. Okay. Then next for the X input, probably I need to scroll all the way back up and then click on that label, Shift Control down arrow, and that'll highlight all of my X data. All right. I want to press labels. Labels means that when I clicked on my input range, I included the label. And you do want to do that because it makes your output look nice. The output range, I like to go ahead and include my output on the same spreadsheet. You can use a different spreadsheet by just doing new workbook. If you want to use the same spreadsheet, you got to tell it where you want it. So I'm going to put it below all of my data. So I'm just going to put it right here. Okay. Now, I'm going to include my line fit plot. All right. I'm going to press OK. Okay. So what am I seeing here? If I double click, it'll make all these better size so I can look at it a little clearer. This right here is the ANOVA. You see it in the output, it gives me the ANOVA. This is exactly the same table that I just drew and discussed. My regression degrees of freedom is 1. My residual, I had 187, because remember the first column is the label, so I have 187 countries. So 187 minus 2, which is 185. 187 minus 1, which is 186. Okay, the sum of squares, very good. They calculated it for me because that would be time consuming to calculate it myself. And the mean sum of squares, right? So they took this one and then divided it by that one. They took the sum of squares residual and divided by the degrees of freedom to get the mean sum of squares. The F is just the quotient of these two. So it's the regression divided by the residual. That's the F statistic. Notice this is a huge number, right? Which suggests that this F distribution is not very good. And then we do see that very low p-value. Remember, e to the negative 19 means that you're going 19 places to the left for, you have a bunch of, you have 18 zeros and then a 4, 6. So it's 0.000. It's very small, right? So this p-value is very small, which will lead me to reject my null hypothesis, right? And I'm going to say that there is a significant linear relationship between income and life expectancy. Okay, and then I can see here the estimates of my coefficient and the estimate of my intercept. So this is B0 and this is, or B0, and this is B1. Okay, and I should also have a plot somewhere. Let me see. Sometimes they throw it up top somewhere. Let's see if I can find it. There it is. Okay, you kind of have to look around on your sheet to see where they put it. So we do see this plot, okay? And the orange is the predicted life expectancy, and the blue is the is the actual observed life expectancies. Okay, and we do see something kind of interesting happening here, and we'll have to explore this later in future videos. But notice that the variability around this line, it may or may not be consistent, right? Is this variability around the line here the same as the variability over here, right? And remember, that is a model assumption that you have homogeneous variability. So is this a good fit? Now, we found that there's a significant linear relationship, but let's not fall into the trap of saying that this is definitely, a good quality fit. We don't know that yet. We need to explore that later as we continue this course.